Section 10.2, Checking Conditions for a Multiple Regression Model, Video 1. In the previous section, 10.1, we were introduced to the concept of a multiple regression. And to put it simply, the difference between a multiple regression and a simple regression was the number of explanatory variables. For example, when we reviewed regressions from section 2.5 and 2.6, we were only considering one explanatory variable trying to justify one response variable. For example, can we use the price of a bill to predict the tip for a waitstaff member at a restaurant? In that case, it's a simple regression because the only explanatory value was the bill. But there could be other factors that could explain the tip, such as the number of patrons in the party, such as the length of time from the time they entered the restaurant until the time they were sat down, such as the quality of food. Which reminds me, in one of the problems I assigned you, and I don't think I put it on a homework quiz, there was a qualitative variable, I believe it was gender, which is hard to represent as a quantitative variable. You can represent a qualitative variable quantitatively by coding it. For example, and we'll get to this in a second, but for example, if we said that X measures gender, we could say X equals 0 means male, and X equals 1 means female. So we just come up with a numerical code to turn it from a qualitative variable to a quantitative variable, and then we can interpret it as such in the context of a regression. But I digress. Previously, we talked about simple regressions, and then in the previous series of videos, we talked about multiple regressions where there could be multiple explanatory variables. We interpreted slopes, we test slopes, we test effectiveness of individual predictors, we tested the model as a whole using ANOVA procedures. So we did all the same things we did previously with simple regressions. So to wrap up this discussion and this course, we're going to talk about what could go wrong for simple regressions. We're going to check conditions for a multiple regression, but we're going to make an analogy to what could go wrong for a simple regression. So back on page 584, I believe this was in chapter 9, there's some illustrations about what could go wrong for a simple regression. In other words, things that if you saw visually in a scatter plot, you should not consider using a linear regression. One of the things that could go wrong is that your scatter plot is curved. So maybe you have some points that start out high, and then they kind of dip down, and then they start going up, like that. Now, any set of points in a scatter plot has a line of best fit, but whether or not it's appropriate to use a linear regression depends upon things such as curvature. With curved data, you shouldn't use a linear regression. I would expect the correlation for this to be rather small, close to 0, indicating a very, very weak linear association. The second thing that could go wrong is that you could have increasing variability, meaning that at the beginning of your line of best fit, your points are relatively close to the line, so small residuals. But as you move outwards, the residuals start increasing, thus increasing the variability in your response variables. And one way that you can spot increasing variability is to draw what I would call a floor and a ceiling line. The ceiling line for this one would be up there, the floor would be down here, and the further out they go, the further apart they get. So that's a way that you can indicate increasing variability, another instance in which you would not want to use a linear regression. And of course, outliers, they always cause trouble. You may remember the example where we had a bunch of dots representing the number of drinks per week people consume, and somebody can claim they consumed a ludicrous amount. We had to zoom out really far to catch that outlier, making the rest of the dots look like they were on a line. These dots might not be very linear. They might be a big blob with no linearity at all. But if you have an outlier that you have to zoom out to capture, then these might look more linear than they are. So the presence of an outlier says you should be careful. It doesn't mean you shouldn't use a linear regression, but you might want to consider the scatter plot without the outlier. So why are we reviewing this? Well, we want to answer the same question, what could go wrong for a multiple regression, multiple linear regression? So how could we spot these things that could go wrong for a multiple regression? Well, here's the problem. In a simple regression, you have one x and one y, one explanatory variable, one response variable. So you only need two axes. So you need a two-dimensional picture. One dimension in the x direction, one dimension in the y direction. But in a multiple regression, we have multiple explanatory variables, multiple x's, x1, x2, x3, etc. If we only had x1 and x2 and the y, then we would need a three-dimensional picture. And I can kind of sketch a three-dimensional picture of a scatter plot and a line of best fit. But beyond that, I don't know what to do. We saw one multiple regression in the previous series of videos that had four explanatory variables, the one about the printers, and a response variable. So in order to sketch that scatter plot and see the line of best fit, we would need a five-dimensional picture, have fun drawing that, in order to analyze it for curvature, increasing variability, or outliers. So we seem to have reached a breaking point where we can't do the same things for multiple regressions that we did for simple regressions, namely analyze a picture to determine whether or not a linear regression is appropriate. However, there's a way to fix it. There is a way to get a two-dimensional visual of a multi-dimensional scatter plot to check for these conditions, and I'll show you what they are in the next video.